From mastering thermodynamics but not feeling when a bearing's about to seize to designing assembly sequences but not hearing the machine whisper it's running wrong to calculating material tolerances but not smelling when lubricant's degrading. This is what factory workers knew that no engineer could learn in school. But first, let's talk about the knowledge nobody wrote down, the stuff that lived in calloused hands and sharp ears, the invisible curriculum that turned textbook theory into actual production. 'Cause engineers designed the systems, sure, but workers, they made them actually work. And for decades, maybe centuries, companies ignored this, hired fresh graduates with degrees and confidence, sent them to the floor, watched them fail, then wondered why production dropped when the old guys retired. So, we're breaking it down tier by tier, from basic sensory tricks to complex system knowledge to catastrophic failures that could have been prevented if anyone had listened. Let's start with the basics. The stuff you can't teach in a classroom. Picture a machine shop in 1920s Detroit, the air thick with metal dust and cutting oil. And in the corner, a machinist stands at his lathe, hand resting on the spinning chuck, eyes half closed. He's listening, not to music or conversation, to the machine, 'cause that high-pitched whine coming from the cutting tool, it's telling him the blade's getting dull, the slight vibration in the frame. Bearings need grease in about 2 hours. And that smell kind of sharp and metallic, the coolant's running too hot. Try teaching that in Mechanical Engineering 101, 'cause this is the invisible curriculum, the knowledge that lived in workers' hands, ears, and noses. And it was everywhere. The welder who could feel heat distribution through thick leather gloves, knowing exactly when penetration hit the sweet spot without ever checking the backside of the weld. The textile worker who detected thread tension by touch alone, catching defects before they ruined entire bolts of fabric. The paint sprayer who adjusted viscosity by eye, compensating for humidity and temperature in ways no formula could capture. These weren't just parlor tricks. They were biological sensors running pattern recognition algorithms before computers existed. A machinist didn't need a micrometer to know when tolerance was drifting. He heard it in the pitch change, felt it in the subtle resistance against the tool, saw it in the way chips curled off the workpiece. And the craziest part? Most of them couldn't explain how they knew. Ask a veteran lathe operator how he knows when to back off the feed rate, and he'd shrug. Just feels right. Ask a die caster how she times the pour, and she'd say, you just know. It wasn't mysterious or magical. It was pattern recognition built through 10,000 repetitions. Muscle memory married to sensory acuity. But here's what made engineers uncomfortable. These workers were making micro-adjustments that improved quality, prevented failures, and saved money. And they were doing it based on feel. Not calculations, not specifications, feel. The steam fitter who knew by sound when a valve needed replacement weeks before it failed catastrophically. The glass blower who saw temperature variations invisible to pyrometers. The toolmaker who felt microscopic burrs that would ruin precision assemblies. Come on, you gotta respect that. And this wasn't limited to skilled trades. Even supposedly unskilled factory workers developed incredible expertise. The assembly line worker who spotted paint defects at full production speed. The packaging operator who knew by weight when a box was missing components. The forklift driver who sensed load balance issues that would cause tip-overs. Management called it intuition and dismissed it. Workers called it knowing your job. Either way, it was sophisticated knowledge that couldn't be captured in training manuals or standard operating procedures. It lived in the body, in the senses, in neural pathways carved by years of repetition. And these weren't just parlor tricks. 'Cause When engineers ignored this knowledge, things got expensive, fast. Meanwhile, fresh engineering graduates were arriving at factories with brand new degrees and unshakable confidence. Armed with calculus, thermodynamics, and material science textbooks, they marched onto the shop floor ready to optimize everything. And production immediately tanked, 'cause in the early 1900s, Frederick Taylor and his disciples rolled out scientific management. The idea? Break every job into measurable tasks, time them precisely, eliminate wasted motion. On paper, it was genius. Workers would follow the one best way, determined by engineers with stopwatches. One problem: workers already knew the best way. The machinists had shortcuts that were actually faster than Taylor's optimized sequences. The forge workers knew this batch of steel ran hotter than the last, so they adjusted timing on the fly. The lumber mill operators could read grain patterns that told them exactly where boards would split. But the engineers didn't ask. They measured, calculated, and issued new procedures. Production dropped 30%. Talk about a degree in expensive lessons. Turns out, all those inefficient movements workers made, they weren't wasted motion. They were compensating for variables the engineers hadn't measured. The extra pause before tightening a bolt, letting metal cool to the right temperature, the unnecessary repositioning of a part, accounting for material inconsistencies that specs ignored, and this pattern repeated across industries. A chemical plant hired engineers to redesign their mixing process. The new system looked perfect in theory, failed spectacularly in practice. Why? The veteran operators knew that humidity affected reaction times, so they'd been making tiny adjustments all along. The engineers assumed lab conditions. Rookie mistake. In a textile mill, management replaced an experienced foreman with a technically trained supervisor. The new guy followed the manual exactly. Reject rates tripled, 'cause the foreman had known that Tuesday morning's thread shipment always ran looser than Friday afternoons, and adjusted tension accordingly. The manual said, set tension to 7. The foreman knew when 7 really meant 6.5 or 7.5. At an automotive plant, a machinist warned his supervisor that the new stamping press was vibrating wrong. "Instruments say it's fine," the supervisor replied. 3 weeks later, the press destroyed itself in spectacular fashion, taking a production line offline for 2 months. Cost? Several $100,000 in 1920s money. The machinist had been right. He'd heard something in the harmonic frequency that no gauge measured. But companies kept making the same error. They saw workers as interchangeable parts. Plug in anyone who could follow instructions, right? Except the instructions were always incomplete, 'cause they couldn't capture the knowledge libraries workers carried in their heads. The forklift driver who knew the warehouse floor dipped in the northeast corner, so you compensated left on heavy loads. The boiler operator who recognized 17 different sounds the system made, each one meaning something specific. The quality inspector who'd seen 10,000 parts and could spot the subtle indicators that this one would fail in 6 months. None of that made it into training manuals. And when engineers redesigned processes without consulting the floor, they optimized for variables they could measure while ignoring the 100 variables they couldn't. So their improved systems worked great until they didn't. At least those were just expensive lessons. 'Cause when engineers ignored workers in these next cases, people got hurt. Picture a Gulf Coast oil refinery, early morning shift, 1950s. An experienced operator walks his rounds, checking pressure gauges and temperature readouts. Everything looks normal on the instruments. But something smells wrong. He can't put his finger on it. Just a faint chemical odor that shouldn't be there. Sharp, almost sweet. He reports it to the shift supervisor, a college-trained engineer who's been there 6 months. "Instruments read normal," the supervisor says. "Probably nothing," the operator insists. "Something's off. I can smell it." The supervisor checks his charts again. Temperature, pressure, flow rates, all within spec. He dismisses the concern. 2 hours later, a gasket fails. Volatile hydrocarbons leak into a processing unit. The operator smells it immediately, hits the emergency shutdown, evacuates the area. Turns out a seal had been degrading slowly, releasing trace amounts of gas that sensors weren't calibrated to detect at low concentrations. But a human nose? That picked it up just fine. The operator had prevented what could have been a catastrophic explosion, not through instruments or procedures, through a sense honed by years of exposure to normal operations, developed to the point where wrong registered at a molecular level. Come on, you got to respect that. And this wasn't unique. Coal miners developed the same spider sense for mountain behavior. They'd listen to timber supports creaking under load, reading the stress patterns in those sounds. An experienced miner could tell when a shaft was about to collapse hours before it happened, not from engineering calculations, from pattern recognition built through thousands of shifts underground. When supports creaked in a certain rhythm, you evacuated. When the mountain went quiet after noise, you ran. The rock was telling a story if you knew how to listen. Steel mill workers read metal composition through color and spark patterns. Drop a piece of high-carbon steel on a grinding wheel and it throws short, explosive sparks. Low-carbon steel, long, flowing trails. Experienced metalworkers could glance at spark patterns and know if the composition was wrong, catching defects that would cause structural failures in bridges or buildings. One veteran steelworker noticed something off about a batch headed for construction girders. The sparks looked weird. Management tested it. Wrong alloy entirely. Would have failed under load, potentially collapsing a building. The workers saved lives by seeing something instruments missed. But here's where it gets frustrating. Factory safety managers kept dismissing these warnings. Workers would report concerns based on sensory cues, and management would check their instruments, find nothing wrong, and ignore it, until something broke. A packaging plant worker insisted a conveyor system sounded wrong. Supervisor said the maintenance log showed it was fine. 3 weeks later, a bearing seized, the conveyor belt jumped track, and 2 workers got injured. The sound the worker had heard? Metal fatigue in a support bracket that visual inspections had missed. At a chemical plant, operators warned that a reactor vessel was behaving strangely. Engineers ran diagnostics. Everything tested normal. A month later, stress cracks appeared in the vessel wall. Shutdown and repairs cost millions, and they were lucky it hadn't ruptured under pressure. The operators had sensed something through subtle changes in vibration and temperature patterns. Their bodies had detected the early warning signs that instruments couldn't measure. And the pattern kept repeating. Workers with years of experience would flag problems early, management would trust their instruments over human intuition, and preventable disasters would happen. So if worker knowledge could prevent catastrophes, why didn't anyone write it down? Here's the thing. They tried. It didn't work. Why not just make a manual? Document every little thing the experienced workers do, step by step. Problem solved, right? Not even close, 'cause in the 1960s, NASA tried exactly this with the Saturn V rocket. After the Apollo program ended, they wanted to preserve the ability to build these massive machines. So they documented everything, thousands upon thousands of pages, blueprints, specifications, assembly procedures, quality control checkpoints. If it could be written down, they wrote it down. Decades later, when there was talk of reviving Saturn V production, engineers pulled out those documents and discovered something terrifying. They couldn't rebuild it. The documents captured what to do, but not how to do it. The master craftsmen who'd actually built the rockets had made countless micro-adjustments during assembly. They'd compensated for material variations, environmental conditions, tooling quirks. They'd developed a feel for when a weld looked right, when a seal seated properly, when tolerances were drifting. None of that made it into the manuals. This is what philosopher Michael Polanyi called tacit knowledge, the stuff we know but can't articulate. "We know more than we can tell," he wrote, and he was absolutely right. Japanese auto manufacturers ran into the same wall in the 1980s. Toyota's production system was famous for quality, so they tried documenting it, creating training materials for new plants, step-by-step instructions for every task. But workers trained on those materials consistently produced lower quality than workers trained on the factory floor in Japan, even when following identical procedures, even when using the same equipment. Why? Because the Japanese workers were making micro-adjustments the manuals didn't capture. A worker installing door panels would adjust pressure based on ambient humidity. Another worker welding body seams would compensate for slight variations in metal composition between batches. A paint technician would modify spray patterns based on temperature and air movement. These adjustments were unconscious, automatic, built into muscle memory through repetition. When researchers asked workers to explain what they were doing differently, they couldn't. "It just feels right," was the most common answer. Companies tried everything. Detailed videos, slow-motion photography, having master craftsmen narrate their processes while working. But when new workers watched the videos and followed along, they got maybe 80% of the way there. The final 20%? That required 10,000 hours on the floor, 'cause the knowledge lived in the body. In pattern recognition, networks built through repetition, in the ability to process dozens of variables simultaneously without conscious thought. A master machinist wasn't thinking about feed rates and cutting speeds while working. He'd internalized those calculations to the point where his hands just knew. Try teaching that through a PowerPoint presentation? Engineers discovered this the hard way when they tried to automate factory processes. They'd study what workers did, break it down into steps, program robots to replicate those movements. And the robots would execute perfectly, producing garbage. Turned out they'd automated the easy 80%, the repetitive mechanical parts. But that final 20%, the judgment calls and real-time adjustments, robots couldn't handle it. The variables were too complex, too contextual, too dependent on sensory input that machines couldn't process. So factories ended up in a weird hybrid state. Robots handled repetition, humans handled the parts that required feel, and companies finally started to realize what they'd been ignoring. That the guy on the floor with 30 years of experience might know something their Stanford-trained engineers didn't. All right, enough theory. Let's get specific. 'Cause what workers actually knew would blow your mind. Here's what they knew. First, material behavior. How metals feel different on humid days. How steel expands just enough in summer heat that tolerances drift by thousandths of an inch. How wood grain doesn't just dictate cutting direction, but changes hour by hour as moisture content shifts. How rubber compounds react to temperature swings that engineering models didn't capture because the models assumed controlled lab conditions. A machinist working with aluminum knew it behaved totally different at 6 a.m. versus 2 p.m., not because the metal changed, but because shop temperature climbed 15 degrees by afternoon. So he'd adjust feed rates throughout the day without thinking about it. His hands just knew, Second, machine personality. Every lathe, every press, every drill had quirks. This one pulls left after warming up. That one needs an extra half-second dwell time. This spindle whines at a specific frequency 2 hours before it seizes. That hydraulic press has a sticking valve that responds better if you cycle it twice before the main operation. Workers knew their machines like people. They'd pat a temperamental press and mutter, "Come on, don't do this today." And somehow that intimate knowledge of mechanical personality prevented breakdowns that scheduled maintenance missed. This is absurdly sophisticated when you think about it. Third, sequence timing. When to apply pressure, when to wait, when to force it. A glass blower knew the exact moment molten glass reached the right viscosity for shaping. Too early and it cracked. Too late and it wouldn't form properly. The window was maybe 2 seconds. No thermometer could tell you when. You just saw it in how the material moved. Metal workers knew when to quench hot steel based on color. But not just color, movement, how the piece glowed and shifted. Books said cherry red, but cherry red under fluorescent lights looked different than under natural light. Experienced workers compensated automatically. Fourth, environmental compensation. Shop temperature, humidity, time of day, even seasonal changes. A furniture maker knew oak behaved differently in winter versus summer, not just expansion and contraction, but how the grain cut, how glue set, how finish absorbed. He'd adjust techniques seasonally without conscious thought. Press operators knew that barometric pressure affected hydraulic systems. On low-pressure days, they'd increase cycle times slightly because fluid compression rates changed. The maintenance manual never mentioned this, but operators figured it out through thousands of cycles. Fifth, failure prediction. Recognizing the sound of trouble 2 hours before catastrophe. A bearing doesn't just fail suddenly. It tells you it's dying. First, a slight roughness in the rotation, then a barely audible tick, then a whine that grows slowly louder. To an untrained ear, these sounds blend into normal factory noise. But a veteran machine operator heard them like alarm bells. They were running predictive maintenance algorithms in their heads before computers existed, processing vibration patterns, temperature changes, sound frequencies, and visual cues simultaneously, integrating data across multiple senses to build a picture of machine health. A maintenance worker once told a researcher he could predict a motor failure 3 days out. How? Can't explain it, just something about how it sounds and feels. When they hooked sensors to that motor, turns out he was right. But the sensors needed sophisticated analysis software to detect what his brain processed instantly. And the craziest part? Companies threw this knowledge away. On purpose. So, naturally, corporate geniuses decided to fire everyone with experience. The 1980s and 90s saw a massive manufacturing exodus. Companies looked at their balance sheets, saw high labor costs, and made what seemed like a logical decision. Move production overseas where wages were lower, lay off expensive veteran workers, hire cheaper replacements. After all, anyone could follow instructions, right? Turns out, the instructions were incomplete. American companies offshored production to factories in Mexico, China, Southeast Asia. They shipped over their blueprints, their specifications, their quality control procedures. Everything was documented, everything was measured. This should have been straightforward, except quality immediately tanked. New factories struggled for years to match the output of the plants they'd replaced. Reject rates ran high, production speeds lagged, equipment broke down more frequently, and American engineers flew back and forth trying to figure out what was going wrong. The documentation was perfect, the equipment was identical, So why wasn't it working? Because the documentation had captured what to do, not how to do it. All those micro adjustments veteran workers made, the environmental compensations, the machine personality quirks, none of that transferred. The U.S. Navy ran into this problem with ship components. They'd been manufacturing certain parts for decades. Then the experienced workers retired, and suddenly the Navy couldn't make those parts anymore. The specifications were complete. The tooling existed, but the new workers couldn't get it right. The veterans had carried knowledge in their heads that blueprints couldn't capture. Automotive companies learned this lesson painfully. Japanese manufacturers opened transplant factories in the United States in the 1980s. They brought their processes, their equipment, their management systems, and they brought veteran workers from Japan to train American employees. They figured training would take a few months. It took years, because you can't download 20 years of experience. The Japanese workers would demonstrate a technique, the American workers would replicate it, and somehow the results were different. Quality wasn't quite there. Efficiency lagged. The Japanese trainers got frustrated. "Just do it like this," they'd say. And the Americans would do exactly what they saw, but it wasn't the same. What the trainers were doing unconsciously, the trainees had to learn consciously. And that transition took thousands of repetitions. Boeing discovered this catastrophically with the Dreamliner. They'd always built planes mostly in-house, with experienced workers who knew the quirks of aircraft assembly. Then they decided to outsource major components to suppliers around the world. Brilliant cost-saving strategy. In theory. In practice, it became a disaster. Suppliers delivered parts that met specifications but didn't fit together properly. Boeing workers had always made tiny adjustments during assembly to account for manufacturing tolerances. They'd known where to apply pressure, how to coax parts into alignment, when to use a rubber mallet versus when to check for underlying problems. The new system eliminated that expertise. The Dreamliner ended up years behind schedule and billions over budget. Boeing had to send their veteran workers to supplier facilities to teach them how to actually make the parts work. But by then, many of those veterans had retired or moved on. Way to go, corporate! And this pattern repeated across industries. Companies pursued de-skilling strategies, breaking complex jobs into simple tasks that anyone could perform. The goal was flexibility. Reduce dependence on highly skilled workers, make the workforce interchangeable, except they weren't accounting for the hidden complexity. A job that looked simple, that could be taught in a week, actually required months or years to perform at a high level. Because the surface task was easy, the judgments underneath were hard. By the time companies realized their mistake, the workers were gone. Retired, laid off, moved to other industries, and with them went decades of accumulated knowledge that couldn't be recovered. But hey, who needs human expertise when you've got robots, right? Let's see how that worked out. Picture Tesla's Gigafactory in the mid-2010s. Elon Musk had a vision. Fully automated production, robots handling everything from start to finish. Minimal human involvement. The factory of the future. Production hell, they called it later, 'cause the robots couldn't handle the complexity. Assembly lines moved too fast, then ground to a halt. Quality issues piled up. Turns out, full automation worked great until something went slightly wrong. And in manufacturing, something always goes slightly wrong. Material arrives with subtle variations. Parts don't quite align. Sensors give ambiguous readings. Robots follow their programming perfectly, which is the problem. They can't improvise. By 2018, Musk admitted defeat. "Humans are underrated," he tweeted. Tesla brought workers back to the line. Production finally ramped up. Turns out humans are useful. Who knew? Adidas tried something similar with their Speed Factory in Germany, launched in 2016 with massive hype. Robots would manufacture shoes in high-wage countries, eliminating the need for overseas labor. Fast, flexible, efficient. The factory closed 3 years later. Why? Robots struggled with material variation. Fabric stretches differently. Leather has inconsistencies. Rubber compounds behave unpredictably. Workers had always compensated for these variations instinctively, making tiny adjustments that kept quality consistent. Robots followed specifications. When reality deviated from specs, they produced garbage. Amazon's warehouses show the current state of the art. Hundreds of robots zipping around, moving shelves, optimizing routes. Incredible technology. But walk into any Amazon fulfillment center and you'll see thousands of human workers still doing pick and place. Why haven't robots taken over that task? It looks simple. Grab item, put in box. Easy, right? Except it's not. Items come in infinite shapes, sizes, weights, textures. Some are fragile. Some are oddly balanced. Some are packed weirdly. A human worker sees a box, instantly assesses how to grab it, adjusts grip pressure, compensates for weight distribution, places it safely. A robot, it needs computer vision, force sensors, machine learning algorithms, and still gets confused by unexpected packaging. And that's just the mechanical part. Human workers also catch errors. Package feels too light? Something's wrong. Box is damaged? Don't ship it. These judgment calls happen hundreds of times per shift, invisible to management but critical to operations. AI can optimize delivery routes all day, but it can't feel when a package is packed wrong. So we've ended up in a weird hybrid state. Factories automate the repetitive, predictable parts. The stuff that's truly repetitive. But the tasks that require judgment, adaptation, sensory integration, still human. And here's the uncomfortable question hanging over manufacturing. As older workers retire, are we losing critical knowledge faster than we can capture it? Some companies are finally waking up. They're scrambling to document expertise before it walks out the door. Filming experienced workers, recording oral histories, creating apprenticeship programs that pair veterans with rookies. But they keep hitting the same wall. The tacit knowledge problem. You can capture what people do, but not always why or how they know to do it. A semiconductor plant in upstate New York faced this recently. Their most experienced technician retired, 30 years on the job. They'd interviewed him extensively, documented his procedures, created training materials. 6 months later, production quality dropped. Little problems the veteran had prevented started appearing, and the new technicians couldn't figure out why. The documentation told them what to do, but it didn't transfer the veteran's ability to read the process, to sense when something was drifting before measurements confirmed it. The current debate isn't really about robots versus humans. It's about what happens when we automate before we understand what we're automating. When we eliminate jobs before we capture the knowledge those jobs contained. So, what's the lesson here? Honestly, it's pretty simple, but we keep forgetting it. Here's what we learned. Formal knowledge and tacit knowledge are both essential. One doesn't replace the other. Engineers design the system. Workers make it actually work, and the best factories recognize this. They don't treat floor workers as interchangeable parts executing instructions. They treat them as experts whose knowledge is different from, but equal to, engineering expertise. 'Cause a mechanical engineer can calculate stress loads and design tolerances, but a machinist with 30 years' experience knows when this particular machine is having a bad day. Both matter. Some companies are finally figuring this out. They're creating communities of practice, where experienced workers mentor new ones on the floor, not just through training manuals. They're filming veteran workers and having them narrate what they're thinking, not just what they're doing. They're building apprenticeship programs that combine classroom theory with hands-on practice from day one. Germany's dual education system has been doing this for decades. Students split time between school and factory floor, learning theoretical principles alongside practical application. They graduate understanding both the engineering and the execution, not just what the blueprint says, but how materials actually behave, not just optimal procedures, but real-world compensations. And it works. German manufacturing stays competitive despite high wages because their workforce carries both types of knowledge. But many industries haven't figured it out yet. They're still racing to automate before understanding what they're automating, still treating floor knowledge as something that can be easily captured and transferred, still assuming that younger, cheaper workers can replace veterans if you just write better instructions. The real skill isn't choosing robots or humans, it's knowing when each matters. Robots excel at repetition, consistency, speed. Humans excel at judgment, adaptation, sensing subtle changes that instruments miss. Smart factories use both. They automate the tasks that are truly repetitive, and they protect, develop, and respect the human expertise that handles complexity. And they remember that a machinist who can hear bearing failure 2 hours early might know something your engineering degree didn't teach you. That the welder who's been running that torch for 20 years has calibrated senses more precise than your instruments. That the veteran operator who insists something smells wrong might be preventing a disaster. Come on, you gotta respect that. 'Cause at the end of the day, manufacturing isn't just about following blueprints.